Okay, we're back and we're looking at some angular momentum, specifically the conservation of angular momentum and how to use it. Just want to run through a couple of examples so we can see how to make use of this really important and fundamental rule in nature. Basically, we have to remember why angular momentum is conserved and when it's conserved. And that's really this part right here, when there's no net external torques acting on the system. Okay, so what does that mean and what does it look like out in the world? We basically have two different ways of finding angular momentum. We've got one version, I omega, when things are actually spinning. Okay, a real object, it's actually spinning within the problem, a collision or something happening to it. The second version is when we have point masses involved. This usually takes place if there's a collision between things, maybe a ball and a bat, or a kid moving along a spinning disk, like on a playground. Or better, if we're looking at planets and orbits. We can treat planets as little point masses going around, and this works really well for elliptical orbits. Anyhow, let's look at a couple of examples here. The first version is going to be if you have just a single object that's spinning. Okay, these are usually kind of the easiest types, if you want to call it that. And it's really governed by the version I omega. And this product, I omega, needs to be the same before and after something happens to the object as it spins. This is what we look at when divers and gymnasts and figure skaters are spinning. If you ever have been on a rotating chair and just pull your arms out and in, and you can actually feel yourself changing the speed as you spin around. Collapsing stars, this is how neutron stars spin so fast when a big star collapses down, and so on. So one real quick video, just want to play a couple seconds from a figure skater who goes into a spin. This is exactly what we're talking about. Okay, with the leg out, she's going slow, and when she pulls the leg in, she's going fast. Okay, so the fact that she's on ice means that there's really no torque acting on her. When her leg's out, she has a large inertia and a fairly small angular speed. When she pulls her leg in, her inertia decreases, and therefore her speed has to increase. So that product stays the same. That's the kind of thing we're talking about here. So one example that I have here is a before and after picture, an overhead view. Imagine that we're looking down on a playground, and maybe a kid is towards the center of a little merry-go-round, little spinning disc, okay, close to the axis of rotation. And so the inertia of your system would be the inertia of the disc, but you have to include the kid. Okay, the kid we can treat as a point mass, so m times that small radius from the axis of rotation squared is the kid's moment of inertia. And then you have perhaps some fast speed that they're spinning around. Now imagine that the kid crawls outwards towards the edge along the radius of the disk. And if you've ever done that, you know that the speed of the disk is going to change. Okay, how should it change? Well, according to this, we have a new inertia. We still have the disk itself, but now the kid's at a different radius, and that's changed the inertia of the system, which therefore has to change the rotational speed. Okay, it'll be a slower speed if the kid moves outward and increases the inertia. If the kid started outward and moved inward, if we run this movie backwards, then the disk should actually speed up, kind of like the figure skater. Okay, bringing her leg in. It's the same physics. Okay, let's move on to the more complicated types where you have a combination of maybe a point mass and a rotating object. This would be like in baseball or softball, bats hitting balls. If you golf, when a golf club hits a golf ball, that's like a rotating stick hitting a little point mass. Pinballs, okay, if you ever play pinballs and those little rotating flaps hitting the ball. You might be sitting on something that can spin, and let's say somebody throws a ball at you and you catch it, okay, with your arms extended. you're going to start to spin. It's going to change your spin. Okay, so these are collisions that involve rotations. So think pinball machines. Here's that little flapper thing. Not even sure what the proper name is for that, but it's a little stick that's kind of twirling around, going counterclockwise, and a ball is moving in towards it. And then afterwards, maybe the little flapper thing stops from the collision, but the ball takes off, and we want to find that final speed, okay, even though it's linear. So here's a case where we have to use both versions. We have to use the MVR sine of an angle for the pinball, okay, little point mass, and the stick part of it is actually rotating, so we need the I omega version. Okay, so in our before picture, our initial momentum, let's say I call this direction counterclockwise. Maybe I call that our positive direction. So the little stick is rotating that way and has that much momentum. Now the ball's moving the other way, so this is still a vector quantity. We have to account for that going the opposite direction. We have the mass of the ball, its initial speed. Okay, it's hitting at a radius 2/3 of the length of the stick away from the axis of rotation, which is up here at the top. And just for the sake of simplicity, let's say that line of motion, when it makes the collision, it hits at a right angle. Okay, so that's going to be sine of 90 degrees. Okay, now afterwards, the stick stops, so it has no momentum of any kind, and the ball's going to take off in the positive direction. So it has the same mass. We're looking for that final speed. It's coming off at 2/3 the length. Okay, that's that same distance right there, relative to the axis of rotation. And the line of motion and the stick from the collision is that same sine of 90 degrees. Okay, so this is going to allow us to find out what that final speed is. Okay, so even though rotations are involved and linear motion, conservation of the linear momentum simply isn't going to it's not going to work here because of that rotating stick. But at the same time, excuse me, we can still work out and figure out that linear motion of the ball afterwards. Okay, I'm not going to go ahead and solve it here, but hopefully you get the picture. Okay, so these are just a couple of examples. Keep in mind, one thing that could come up is this a elastic collision or inelastic collision? In other words, how does the initial kinetic energy of your system compare to the kinetic energy of your system after the collision? We can still do that even with these rotational type problems. Initially, because we're looking at the whole system, we would have to compare the quantity, the rotational kinetic energy of the stick plus the translational kinetic energy of the pinball, and see whether or not that's going to be equal to the final kinetic energy of the pinball. Okay, in real life, that's not going to be the same. In real life, every collision, you're going to lose a little bit of energy to heat and sound and friction and vibrations within the materials and all this. So chances are, these types of collisions will turn out to be at least partially inelastic. Every so often in physics land, you might be given a problem where you're told it's elastic, and that's another equation that we can use to help solve this. We can compare the kinetic energies before and after. Okay, that's just a variation on a theme. The important part here is we're looking at using angular momentum for both actual spinning objects and point masses that are moving relative to an axis of rotation. And we can start to see how this really important law takes hold and how it's applied. Okay, so I hope this helps, and until next time, we'll see you later.